Today we're going to talk about phase diagrams. Phase diagrams are simply a way of representing the different states or phases of matter based on their temperature and pressure. For instance, if you look at this diagram, you'll see that the temperature is increasing on the x-axis, the pressure is increasing on the y-axis, and the different states of matter, solid, liquid, and gas, are represented. Now, in chemistry, I've probably never met a chemistry teacher that didn't refer to this kind of diagram as a butt diagram. Chemistry teachers are kind of a strange lot, and some of us are way weird, but if you look at this, it kind of looks a little bit like a butt, and that simply helps us remember where the different states of matter are located. The solid is located, that one just makes sense. It's at the low temperature, higher pressure. That would be a solid. The liquid is next to it as the solid's melting and turning into a liquid as the temperature is increasing. And then down here is where the gas is produced. So, like I said, butt diagram. Please don't refer to it as a butt diagram on the AP test. It's a phase diagram on the AP test. So on this diagram, there are different spots or regions that we need to be familiar with. One of these is the triple point. The triple point is way cool. The triple point is the point, the exact temperature and pressure at which a solid, a liquid, and a gas can exist in equilibrium. What does that mean? It means at that point we may have a solid melting, liquid freezing, the liquid boiling, the gas condensing, all of those things happening, but the total amount of solid, liquid, and gas does not change. It won't appear that you're getting any more or less solid or liquid. So again, the point where all three of those states of matter can exist in equilibrium. Now, the critical temperature is the temperature at which, above this temperature, there is no conventional liquid. There's no liquid above this temperature, no matter how high the pressure is. Now, that gives us some kind of funky properties for substances above that temperature. We often refer to these as supercritical fluids, and a supercritical fluid, again, can have some unexpected properties. One of these is that they can often dissolve or act as a solvent to dissolve some normally insoluble materials. Used to, they would decaffeinate tea and coffee, for instance, using some fairly harsh chemicals, and I can remember we used to worry about what kinds of chemicals were left over as residues in the coffee and tea. But many companies now use supercritical carbon dioxide to extract the caffeine from the coffee. It just dissolves the caffeine and carries it off, which is a super clean way to do that. We also have something called the critical pressure, which is the pressure at the critical point or at the critical temperature. And then we have what's referred to as the critical point, and that's where those two meet. The critical point is the temperature, the pressure and temperature. Again, I'm not saying this very well at this point, but the point where the critical temperature and the critical pressure meet is the critical point. Now let's look at this diagram. This is a diagram of water, a butt diagram, if you will, for water. And in this diagram, we see the same kinds of points we had on the other one. For instance, what is the triple point on this diagram? Hopefully you pointed it out and you came up with the fact that it's at point 0, or O probably. At point O is the triple point. The critical point then, again, is where there is no liquid above this temperature, so it's going to be way up here at point A. That's going to be our critical point. And we can tell a lot of things about what's happening to the states of matter as we change pressure or change temperature. For this first example, the temperature, what change occurs when the temperature at 1 atmosphere goes from -10 to 50. Remember, 1 atmosphere is 760 millimeters of mercury. So looking up here, if we look at 760 millimeters of mercury right here, and we go to about -10, now this diagram is not to scale, but -10 would be somewhere in this range right here. And if we're looking at moving that temperature from -10 to 50, it would be somewhere over in this area. So we're moving from the solid water to the liquid water, from a solid to a liquid, so that would be melting at that point. Now what about the pressure changes from 0.005 to 10 when we're at 10 degrees? So let's go to 10 degrees, and again, it's not to scale, but let's say 10 is somewhere in this region. And we're going from 0.005 millimeters of mercury, which is almost zero, so we'll say this point we just drew is almost zero at that temperature, and we're going up to 10 millimeters of mercury. Well, we don't know exactly where that's going to be. Again, it's not to scale, but it's going to be above the 4.579. So somewhere in this region, we know at least that we're moving from the gas state to the liquid state. And from gas to liquid, that's our condensation. So we can get any kind of change like that. Let's say we're going from a solid down here straight to a gas. That would be our sublimation. Maybe we're going from liquid to gas. There's our vaporization or boiling, etc. So changing around the temperature and pressure, we can look at that diagram and determine what kind of phase changes we're going to have at those, under those conditions. Now, what about for the densities of solids and liquids? You wouldn't think that a diagram like this would tell us about the comparative density of the solid and the liquid for a particular type of matter, but it does. And it's all about the slope of the solid-liquid border or interface. If you have a positive slope for that interface, and that interface up here is this interface right here, that's the border. If you'll notice, in this particular case, it's a negative slope. So this is going to be an example for water down here. And look at what that tells us. A positive slope is going to mean that the solid is more dense than the liquid, and it's actually going to sink in the liquid, which is the most common. But we have no problem with our ice cubes, our solid ice floating on top of our water. We're used to seeing that, and we don't really realize how very odd and strange that is. But that negative slope on that diagram we just looked at tells us that the liquid state is more dense than the solid state. The solid state, the solid ice in this case, is going to float on top of the liquid. Now, I don't know why I've got common after it. It should read uncommon, because this is a very uncommon condition for the solid to actually be less dense than its liquid. So looking back on the previous example, we see that this particular slope is a positive slope. And since it is a positive slope, what does that tell us? It tells us that in this case, the solid is more dense than the liquid and would actually sink in that liquid. So that's just another piece of information that we can get from a phase diagram.